Hi and welcome to this channel. In this video I'm going to solve a geocache challenge. My neighbor is into that geocaching stuff, and he also knows I like the occasional math riddle, so he comes to me with stuff like that. This video is called Throwing Stones in Germany because it involves throwing stones in Germany. Sounds logical, right? It's a basic physics problem about motion. Mr. Newton would have liked it. I like to use a class called maxima, link in the description. CAS stands for Computer Algebra System. It's free and it's quite powerful, and it's a great tool to use if you study math or physics. There's also a link to the WX Maxima file and a PDF made with WX Maxima. WX Maxima is a GUI for Maxima. Spoiler alert, if you want to try to solve this yourself, you obviously shouldn't watch this video, or at least not until you've given it a try. So, let's have a look at this.
So we're going to throw stones in Germany because this problem is originally stated in German and can be found here. So if you go to there, you see Lost Place, Kloster, Ruin, Schwarzenbroich, and the actual problem is actually stated here. For those of you who don't speak German very well, you can just throw that URL in Google Translate. So if I go translate Google, put that in to English, and then again look here, that should be enough to get you on your way. Now, so the question is, you get a set of coordinates, and then they say from there it's only a stone's throw to the monastery ruins, but the cache is outside the complex, and the throwing parabola of a stone that is thrown at a height of 2 meters in the direction of 30 degrees. What he means is you face north and then turn 30 degrees to the east and throw your stone at a speed of 69 meters per second and a throwing angle opposite of the horizontal of 32 degrees, and that parabola ends directly at the cache. Also, the terrain drops to the cache with an average of 4%, which means 4 meters height difference on a 100 meter path length. You can neglect the air resistance, and acceleration due to gravity is 9.81 meters per second squared. And then you need to find the right coordinates where the stone hits the ground, so something like this. So equations for velocity and distance. Well, we know that velocity is the derivative of distance over time, and acceleration is the derivative of speed over time. And so the integral of speed is the integral of a times dt, and the integral of ds is the integral of v times dt. So if we do dv over v0 to v0 being the starting speed, and set that equal to a times dt from 0 to t, we get v minus v0 is a times t, or v is v0 plus a times t. Same thing if we do that for the integral of distance, ds, from s0 starting distance to s. We set that equal to v times dt, and v was this, so v0 plus a times t dt. Between 0 and t, we get s minus s0 is t times v0 plus at squared over 2, or s is t times v0 plus at squared over 2 plus s0. Then what's also given is the angle, 32 degrees, that is 8p over 45 in radians, a speed of 69 meters per second, g is 9.81 meters per second squared, and the height or the distance in y direction 0 is 2, so the starting height is 2. Now we're going to split, of course, the speed and everything else into x and y components. So then you get parametric equations for distance s and x and y direction. Since we do not have any acceleration in the x direction, only in the y direction, where it's equal to g, we end up with, if we first do Vx is V times the cosinus of alpha, so this 32 degrees, and Vy is then V times the sine of alpha. We get that the distance over the x direction is V times x times t, Vx times t, sorry, not times t, so Vx times t, and the height Sy is Sy0 plus Vy times t plus minus 1/2 gt squared. The minus is because the g is of course going downwards. And then we have that slope where they talk about of 4%, so it's minus 4 over 100 times x. Now if you want to get the Cartesian formula for the parabola, you have to get rid of t in those two. So from the first one, the distance x is Vx times t, you can get t, which is the distance x, over Vx, and then you fill that in is in Sy of t, so this t f and x is then just Sy of this t. So for fun, you can calculate the maximum height and where it occurs. And to calculate a maximum, we need the derivative of the function to be equal to 0. So the derivative of x to x equals 0, and then solve for x, which gives us, well, that's the derivative, which gives us the x coordinate of the highest point is 218 meters and something. The time, we can get that from here, is 3.72 seconds, and the height or the distance in the y direction at that time is 70 meters and a bit. Some graphs, if you look at the path of the stone, so this is your equation, and that's your equation for the slope, so the slope is in red, and that is your path of your stone. So you can see clearly, as we calculated already, that at 218 meters, something like that, we get the highest point, and that's about 70 meters, 70.14 meters. Obviously the stone hits the ground here where those two meet, and that's about, I would say, 470 something and about 18 maybe meters. If you plot the height of the stone over time, you get a similar graph, obviously, but it's not the same thing because here you have time, there you have distance. Then you can see that the highest point is reached about 3.7 seconds, like we calculated. The stone hits the ground at about 8 seconds, and that is at a height of somewhat like 18 meters below starting point. You also see this 2 meter starting point of the throwing stone, so it doesn't start at 0, but it starts at a height of 2 meters and then hits the ground here. And obviously, I said that already. Distance of the stone over time is just Sx from t, and that's 58.5 times t. That's obviously just a straight line, which after 8 seconds ends at about, well, 470 meters. Velocity of the stone over t in the y direction, that goes down. So if you just do it for the x direction, this is a straight line, so v is 58 meters per second, 58.5. Y is a straight line, so it goes down, so your speed goes down, goes down, goes down, passes 0. So this is the highest point of your graph, or the highest point the stone reaches, and then it starts to go down again. Acceleration of the stone over t in the x direction is 0, and acceleration of the stone in the y direction is constant and equal to minus g. So if you graph that out, second derivative in the y and x directions. And I see I need a space here. So where the stone hits the ground obviously is where f and x is equal to the slope of x. So you have to put them equal and then solve for x, which will give you two values, a negative one, which is obviously nonsense. You go back in time then. And a positive one, which is 467 meters and a bit. So that's where the stone ends. And f and x, or the slope at that point, same thing, is minus 18.68 meters. So about 20 meters lower than the stone started because of the 2 meters extra. So you can then calculate the value of t. Remember that t was, where did I get that? Vx over vx. So it turns out to be 7.98, so almost 8 seconds, like you saw in the graph. And then if you put that in the parametric equations, of course you have to have the same values as you got here. Now, getting the coordinates of this thing, well, we were given those. So that's the start, 50 degrees north and 46.255 minutes, and 6 degrees point north and 21.98 minutes. So you divide these two decimal minutes by 60 and add that to the degrees, which gives you a longitude of 6.363 and so on degrees, and a latitude of 50.77 and something. Now he also says a stone that is thrown in the direction of 30 degrees, so you need to split the distance in the longitude and latitude part by multiplying the x-coordinate where the stone hits the ground with respectively sinus and cosine of 30 degrees. So I put my x-axis this time to the east, and the y-axis is to the north. So we end up with 2.33 meters, 0.5 to the east, and 404.5 meters to the north. That's where our stone lands if you look at the or if you start from here. So now we have a number of meters in east and north direction. Obviously we have to convert that to degrees, and the way to do that is simply calculate how many meters we have per degree on the globe. That is, if we think of the Earth as perfectly round, spherical, which is, of course it isn't, but it's a close enough approximation. So the number of meters we have is 40,000 kilometers divided by 360 degrees, and that turns out to be something like 1,000,000/9. So to convert a length to degrees, just divide by this meters per degree number. So to the north we have dy, so 404 divided by meters per degree plus the starting latitude. For the east it's a bit more complicated because the closer you get to the poles, of course, the less meters you get per degrees. At the poles it's 0. So you have to multiply that number meter per degrees by the cosinus of the latitude where you're at to get the actual meters per degree at that latitude. So we get then dx divided by the cosinus of the latitude times meters per degrees plus the longitude, and that gives you n is 50, so to the north 50 degrees, 0.77 and a bit, and to the east 6.369 and so on. Now the conclusion of this is you shouldn't get into a rock throwing contest with the German, because honestly throwing a rock almost 500 meters far, it's quite impressive. Now there's another way to solve this at the start, that is, so instead of transforming the formulas, the parametric formulas of the stone, you just transform the formula of the slope into parametric equations from Cartesian. So we know the distance is t times vx, so that's also the formula for the slope, which is obviously equal to the x component of the stone. And if you want the y component of the stone, the slope, sorry, you fill in the slope and then that value x of t, or actually the value of 4x in terms of t, so actually it's just the same as t times vx, to get the parametric equations. And then of course the heights of those two must meet. Here you see the parametric plot, so sy and sy of the slope must meet here, and if they do, we can calculate the time where that happens. So we solve the slope y value for time. I used z because I used t already. Must be equal to the height of the parabola at the same time, and then we solve for this time, which gives us two solutions, minus 0.05, which is nonsense obviously, and 7.98, well, almost 8, the same number we got previously. So I call this TP from parametric, and if you fill that in the parametric formulas for the parabola, you get in the x direction 467 meters, same thing as we got before, and the y direction is minus 18.6, so actually about 20 meters lower than the starting point of your stone. And of course, if you fill that in the formula for the slope, you should get the same values, which we do. And from there on, once you've got these two, or actually just this one, it's the same thing for getting the coordinates, of course. And that was it.